In this video, we are going to find all integers n such that n to the power 4 plus xn cubed plus 11n squared plus 3n plus 31 is a perfect squared. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. If this expression has to be perfect squared for some integer n, then perhaps it might match with some expression about n all squared. For this, we can try some quadratic expression like n squared plus an unknown integer multiplied by n plus another unknown integer all squared. And I want this to be as close to this quartic as possible. Now, the coefficient of the cube term, 6, gives a hint that we want this to be 3, so that when we expand this perfect squared, the coefficient of n cubed would be 2 times this unknown, and it has to be 6. We want it to be as close to 6 as possible, so we choose the number 3 as the coefficient of n inside the bracket. Whereas for the last unknown, say the constant term inside the quadratic expression, we can try expand n squared plus 3n plus, let's say, a. We can let this unknown be a for the time being, and we try to expand it. So we have n to the power 4 plus 6n cubed plus 9, which is coming from 3n times 3n, and 2a from a times n squared doubled. So far for the first two terms, it went as planned. N to the power 4, 6n cubed, exactly the same as the given quartic. Now for 9 plus 2a, all multiplied by n squared, we want that to be as close to 11 as possible. So why don't we choose a equals 1 first. So we can continue the expansion. So we know we want this to be 11. And now for the n term, we will have 3n times 1 doubled, and that's 6n. And finally, plus 1. So it's not exactly the same as the given quartic, but we are quite close. Just two of the terms that there's some sort of difference, but for the other three terms, it's exactly the same. Now what happens if I try to change that constant term a bit? Say if I change it to 0 or 2, then let's see. For n squared plus 3n all squared, if I expand, then I'll only have the first two terms to be the same, and the third term will be 9n squared, and in fact this is the last term of this expression. We have no n, no constant in this perfect squared. Now notice that the difference between the given quartic and this perfect squared, the difference is (2n squared plus 3n plus 31). And no matter n is positive or negative, it seems it will be always positive, because if we try to complete the squares, we have 2 times n plus 3/4 all squared minus 3/4 all squared, which is 9/16, plus 31/2. So simplifying, we have 2 times n plus 3/4 all squared plus 31 minus 9/8. So the difference would be at least 239/8, and that's positive. So these calculations tells us that no matter what value n takes, the given quartic is always larger than n squared plus 3n all squared. Now we can also take a look on what happens to n squared plus 3n plus 2 all squared. Now on the other hand, this perfect squared would give the same starting two terms as before, but for the rest of the terms, we have 13n squared is 3 squared plus 2 times 2, and then plus 2 times 2 times 3, 12n plus 4. Now this seems to be larger than the given quartic. Again, the difference will be 2n squared plus 9n, and we have minus 27. So at some point this might be negative. So let's see what we can have. And doing similar calculations, we know that the difference is mostly positive, but there are some rare cases, some very few cases, which the difference could be negative. So we can rule out the negative cases, separating them out, and focus on the majority case first. So what happens in the majority case is that for most of the n, we will have something like n squared plus 3n all squared is less than the given quartic, and its given quartic is at the same time smaller than another perfect squared, which is n squared plus 3n plus 2 all squared. That gives us no choice, but the expression in the middle, if it has to be a perfect squared, then the only choice would be that it equals to n squared plus 3n plus 1 all squared, which from the expansion above is n to the power 4 plus 6n cubed plus 11n squared plus 6n plus 1. And the only case that allows this to happen is that these two terms on the left are equal to those two terms on the right. So solving, we have n equals 10 among the majority case. Now the final question is, where are the so-called minority cases? The minority cases come from when the so-called difference is negative. So when it's negative, two times n plus 9 over 4 all squared has to be smaller than 297 over 8. And simplifying, we have this. And of course, we can try to square it at this point. We have minus 3 times root 33 over 4 minus 9 over 4 as the lower bound, and 3 times root 33 over 4 minus 9 over 4 as the upper bound. If n has to be an integer, then we can use the bound, approximate value of root 33, which is around 5.7 or 5.75 if you like. Then integer possible values for n can only be minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, and 2. To save time, here are the results of the trial on the possible cases minus 6 up to 2. To speed up calculations, I've rewritten the given quartic as n squared plus 3n plus 1 all squared minus 3n plus 30, so that for the square part, it will be easier to calculate by hand. And we can see that all the outcomes are not perfect squares, so the only answer to this problem is that n equals to 10. This is the only solution. Please feel free to share ideas in the comments. Thank you for watching. See you next time.